Good morning, Professor Page.
Good morning.
How are you?
I'm fine, thank you.
Very well. Very good. Here in Mexico, it's too much hot, the weather, and
Still cold or too hot?
hot, too hot,
Ah,
too
first,
hot.
too hot, yes.
But yes, and um, and we have not any rain. And it is too much. How do you say? 30. Yes.
Mm,
Mhm.
yes, so it's hot for this time of year, for sure.
Yes. But it is more than used to be. But um, uh, anyway.
Yeah, well, I remember only a few months ago, it was very cold in Mexico.
Yes, the weather now is changing too much, extremely in Mexico. See. Mhm. Yes. Uh, and how is in your place the weather
Uh,
now?
yeah, now it's uh, moderate. It's uh, the weather here can be about oh, 10 to 15 degrees during the day, uh, but
Mhm.
rainy. Uh,
Oh,
Today, not so bad, but it's the time of year when we get to rain.
oh, okay.
I think today we were going to have a presentation by Dr. Sobczak, I think. Is that
Yes, this was
correct?
programmed in this way. Mhm.
Hmm. So we're just we'll wait for him, I guess.
Yes, we can. I have been. I have continuous working with the idea of um, a categorical presentation of the duality concept in now Grassmann algebras and three-four algebras. Mhm.
Mhm.
I think that there is some too much interesting things around this problem. Then, mhm.
The problem of how to represent Clifford algebra, I think, especially in a categorical way, is something that I never saw completely resolved. Not uh, there's the definition that was done by French, the mathematician Chevalier.
Uh,
Uh,
yeah,
yes, he had a particular way to define Clifford algebras that did not require the notion of symmetric forms, and uh, it was more, I suppose, more purely algebraic. But I think I had some discussions with Zbigniew about this because he had the desire to define Clifford algebras um, using these the string diagrams, using the axioms that are written down in terms of the pictorial language. And I think he was never entirely satisfied with the description that he had.
Yeah.
It was much easier to do this for Frobenius algebras, but for Clifford algebras, it seemed at least some uncertainties as how to proceed formally. But so I think it is an interesting subject, especially if you can relate it to Grassmann algebras directly.
Yes, I have find some literature related with Grassmann algebras, and I think that the starting point using Laver paper, I think it is too much important because it's an excellent starting point for the definition of multigrade algebras. He used some called causal constructions, for the multigrade algebra. And I think that it is too much clear there how we can, starting from lower degree algebra, build the higher degree algebras, like mappings of the module in the category of modules. Then I think that it is an interesting approach for that. Mhm.
Oh, yes. Okay. In your presentation a few weeks ago, your slides had a lot of material, which I think for someone sort of less familiar with category theory, it's quite a few steps, quite a few what to say. It's worth several lectures. You could spread out that presentation over several more lectures, I think, to get the foundations of what you were talking. Yeah, the language especially, that maybe even this concept of a junction, right? The notion that
Yeah. Mm.
and in category theory, I think, as you pointed out quite correctly, it's this notion of duality is strongly connected with the notion of an adjunction, and pairs of the pair of functions in the adjunction that define the adjunction functors. And I think it's very abstract definition in category theory. Of course, category theory has a lot of abstract material, but the beginning point of category theory, everything seems almost elementary. Like when you start with graph theory and so forth, and then you introduce like the ideas of commutative diagrams as a language, in which to express the axioms. And from there things get more and more abstract until you actually have very good examples of how they're used. Like why do we need this concept of a junction? Maybe for me it always seems surprising that you can say anything with such an abstract construct. Like how to make it fit into a subject like Clifford algebras never seems obvious to me.
Sorry, I lost part of this comment, and I think it is too much important.
Yeah. Well,
Mm.
I guess the point is I was trying to make was that it's like the toolkit, like the tools that you develop in category theory seem abstract and very pure in their definitions without any immediate applications. Like it isn't. Most presentations of category theory emphasize that abstraction. That certainly the first papers, McLean and so forth, their papers, I always found them very abstract, but Levere was much better. Like Levere spent a lot of time developing applications of these concepts. But still, I don't know what is the correct balance, like how to introduce this subject, say, to someone like Dr. Sobchak, who doesn't have a very strong background in category theory. He sort of understands, like, it's maybe that it's an important subject and that it can be applied in wide areas, but I think there's a barrier to see how it can be applied, like how.
I think for me the problem is that category theory is like a language that we
Yes.
need to use for speaking or for talking about many subjects in mathematics and physics, and another areas today. But it is a extremely difficult language because it is too much many concepts, and they are difficult to fix and relate with one particular subject. And for example, speaking about the Clifford algebras, in the approach that Professor Garrett used to do, he started even referring to the set of the elements that are the base, the base of the algebra. I think that he started with this set and their properties, and then he put the multiplication table, the product table. But when we start in this way, I think that we arrive to the concept of sets. and then we are working with the elements of the set, and not we are not working in a general way. Then it is difficult to write an abstract approach to this algebra if we refer immediately to the sets elements elements. Then I think that the idea of Laver speaking about a Grassmann algebra, it's a good way of it's a good approach for this problem. And then we can discuss about Clifford algebra like a particular case of the Grassmann algebras. Then I think that this is Clifford algebra is a subset of Grassmann algebras. Then
but
a subcategory.
But the main thing that you add with Clifford algebras is some type of scalar multiplication, right? Something that is like a something that maps the Clifford elements back to the scalars. And the only thing that you have like that in Grassmann algebra is if you introduce both vectors and forms. Right?
Yes.
And so,
yes.
So in a sense, it depends, I guess, how you define the Grassmann algebra, but a Grassmann algebra is usually defined with this as either vectors or forms, but not both vectors and forms. Like not so there is a sense in which what Dr. Sobczak is talking about, and when he talks about this global duality of having two Grassmann algebras, that you need, in a sense, the Clifford algebra is not a subset of a single Grassmann algebra, but rather somehow related to this pair of Grassmann algebras that allows for the operation of insertion, right? That allows you to produce a scalar value.
But I insisted that in the Laver approach, he started the approach for Grassmann algebra, speaking about one operator that is the boundary operation. And then these boundary operations is too much important because is the way that we can go to higher degree algebras, and not only in the scalar forms, but we can do that in vector forms too. Then this is an important point, and with the Kosul constructions, he used the D operator for building higher degree algebras. Then we have in Grassmann algebras two kinds of operators: boundary operator and a differential operator. And with this we can build vectors and forms, multigrade vectors and multigrade forms. And we can connect them, how Professor Osiewicz used to do that, with the evaluation operation. Then in this way, the Grassmann algebra is a global approach to this kind of algebras. And then if we stay in the vector forms, then we are lost in the scalar forms because we put out the boundary operator. Then in Clifford algebra, there is not boundary operation, only exterior multiplication, only that. And then in this way, this is, as I understand this is a subcategory of the category of Grassmann algebras, because we draw an operator, and then because of this, the duality problem is in Clifford algebras is that Clifford algebras are self-duals. Self-duals. But in Grassmann algebras, they are not self-duals. Because
I see.
There is a dual space to the vector space. And then I think that this is this can help to understand the difference between this kind of algebras and put in the in good order this kind of algebras. This is in general my ideas. I put some slides. If you like, I can.
Yes, I think that would probably be good. I don't see Dr. Sokrat hasn't joined us, but Brian is here this morning, I guess. So,
Oh.
you know, so if you do have some slides, sure. Let's look at this subject in more detail.
Yes. Okay. I'm going to look for the slides. Okay, I have here now. Then I'm going to share. Okay, I have too much material here, but I am going to the last slides that we were discussing. Okay, I think that here we have, and only in with the idea of fix this, I am remember how Laver approached the problem of Grassmann algebra, and he started with a affine category that is the starting point for connecting with a graded algebra. Then the first problem is to get an universal universal pair that can help to us to connect the affine space with the category of sets, and then have an algebra built in this category of sets for the affine space. Then, in this way, the first point is that the consideration that there are an operator inside the Grassmann algebra that is the boundary operator. This operator is a differential operation, or better, in a better way, a derivation operator. Then it follows the Leibniz rule, and then this definition for this operator can be seen here. A and B are elements in the affine space, and then the action of the boundary operator gives to us the boundary of each element, with the condition that the more elementary object inside this space are points, and then the boundary of a point is associated with the value 1. That is the lower value for this operator. Then, for example, if we realize the product of 2 points, then we get an arrow or translation vector, and then the boundary of that translation vector give to us the 2 points that are defining the axial vector AB. Then the operation with this boundary operator give to us this translation vector in the vector space. A comment that is important is that Laver expressed that the editors of Grassmann put out this important concept in the work of Grassmann. Then Laver was reviewing the papers, the original papers of Grassmann, and get this important concept in the for the Grassmann algebra. Because he arguments that the editors consider that this operator was necessary because for they all the operations that Grassmann was expressed are only translations. And then the value of the concept of boundary was lost. Okay, this operator is important because it's part of the pair that help to build an universal functor in the language category. Then of category. Then he expressed in this way. If we have 1 point in the affine space, here I represent this point by P, and if we have one morphism in the category that is the operator partial P, then we have with this pair an universal arrow. This universal arrow permits to select one arbitrary point in the affine space that is related with the origin for the vector space. And then with this give to us a 1 degree of the algebra, and this is the starting point. Then
Jesus, can I ask a few questions, just somewhat elementary questions, like when you talk about the affine space, you consider it a category, right? So that the objects in this category are points, I guess, and between points we have these arrows, morphisms, which are something like a path, right? Something like so we think of this in geometric terms by thinking of the geometry of points and then some way of connecting points, like through a directed line segment, for example.
Yes.
But on that, in this category, we don't have any vectors per se. We don't. But the category that you're talking about, the Grassmann algebra, that you construct from this, or that is related to this, as you said, by the construction. When you write, for example, G sub 1 of alpha, that in geometric terms is something that would be directly related to a vector, right? It's an abstract representation of vector, I think.
Yes, I think that it is necessary to fix some ideas here, because the left diagram, the left diagram, that is in the affine category. This is an abstract category.
So,
and then
so maybe it takes some, time to present this category with the point of view of sort of a geometric intuition, right? To say what part of geometry do we represent by this affine category?
Yes, maybe I can write something here in this slide. Wait a moment. I only take my okay. Okay, suppose that first we have the affine category here. And here we have the set category. Then first, in the way that we can build the definition of this A category, we need a function that give that permit to us to associate objects in A with a set, for example. Here I can say this is, okay, P. I'm going to call this P. And here, for example, I have A prime, and then I have here a morphism in the affine category. The problem here is how can I get an implementation of the operation that we need to perform in the A category in the set category. And then I need to do some implementations that are better pictured now in the diagram that I was put before. Then I'm going to erase this. And this is the A category, and this is the Z category. Then I need a functor here that is the G1 functor that take to us from this object A to this object in the Z category G1A. And the same for the object B. But the idea is that I like to take this object here like the universal description of the the universal description of this implementation of this concrete implementation of the category A. And then I need a morphemes here that is, for example, this. I'm going to put the letter F for describe these morphemes that permit to us here to relate these two. And then I have here another object in the Z category that are related with these operations, that is the universal arrow. Then we have a set here that is the object A and the universal arrow A. These together give to us the possibility of build the implementation of any other object in the category. Then this is the idea here. Then we have these two pairs that are an universal pair. For the functor G1. And then when I performs these constructions, then all the objects in the affine category are described in a good way, following this commutative diagram that is in this slide. This is the idea here. Then G1 is a functor, and then an important way is that then I'm going to erase this, okay, and then this operator here acts like a covariant functor connecting different degree algebras. And then we can continue this built-in process at higher degrees. I don't know if this comment is in agreement with your comment, Professor Pesh.
Yeah, the most critical part, I think, of this is that the boundary operator of G1 is scalar, is 1, right? Where I think on your slide you showed this
Okay.
perhaps a little bit earlier, or
no, I think that here,
or even in the definition. Yes, here. Yes, here. So a boundary of a point is 1, right?
Yes, yes. That this is different that the boundary of of a point in the vector space, because in the vector space the boundary of a point is 0, but in the affine space no, because is part of the is one object in this space. I think that this is put in another diagram here. I go back here. Here we have. Then from the affine space, from the affine space, we go to the graded algebra with two functors. Then G1 that takes from affine space to vector space, and after the exterior algebra. Then with these two, I get the graded algebra. And this arrow here is important because this is the forget functor that take to us from the affine category to the set category. Then this denoted by parenthesis 1 is the forget functor.
Yeah, forgetful functor.
Forgetful functor, yes, yes.
Yeah. So in a sense, it generates the free algebra over that.
Yes. But this is generated by the composition of G1 and the Grassmann product. Then I think that there is some more slides here. Okay, here that is another way of seeing this. Because we go from the affine space to the vector space, and then from the this G1, because the degree of the dots is 1, if we apply again the boundary operator, then we get the field of and that is the scalar field that is the implementation. How do you say categorically is the they don't use the word implementation, but representation is the representation of this algebra. And then I think that these slides are important because is here the building process of the Grassmann algebra based in the boundary operator. And this is important because Grassmann algebra got to here, and Clifford algebra stayed here. Then there is an important difference between those. No? And okay. Sorry. No,
I just wonder. For me.
Sorry, I moved it accidentally here.
It's okay. I'm thinking about the.
Yes, I don't.
How to give examples, maybe how to understand this more intuitively without sort of the. Yes, here is good.
Okay. I think that now we can go first to Grassmann algebra. Here is the COSUL constructions that permit to us to build the multigrade algebra. Then we start with a chain complex related to the boundary operator. and then we go with the degree 0 to the degree 1, sorry, degree 0 to the degree 1. I need to this, okay. Degree 1 and 2 and so. And this is getting with an operator that is the x here. Then the idea is that we are taking an element of the of the space, and then with that element, we build this chain complex using this operator. Then we have here a relation between we will this making a mapping of modules in this category. Then we take one module to another module using this map. Then with this, I think that we have the base for the Grassmann algebra, because now we can say, sorry, okay. Here I put the two chains together. That is the chains using the boundary operator and the D operator. This kind of graph used to be made by Professor Rosiewicz many times, in the way of building that all the starting point for this algebra is the scalar field, and starting from the scalar field, we can go to higher order degree of this algebra, but we can go in the reversed way with this. Sorry, there is a mistake here. Sorry, because here we are in the dual.
Oh, yes.
Sorry. Okay, I need the dual algebra. But these two parts of algebra are both part of the Grassmann algebras. And then we can take this like the starting point for look about all the properties of this algebra. Then I think that in category way is almost enough with this. But I think that here I have one more slide that is important, because now we we have here the implementation of this algebra in the category of vector space using the tensor product like universal elements. Then here we have two important things that are the objects, that are the pair that will the universal element. This is this element in the category of vector, and this is an element, an morphism in the set category that permit to us to relate an element in the set category with a bilinear form. Then with this, we can see an important thing about the tensor product, because this tensor product is an operator for building new vector space, but it is used for building and bilinear forms. And this is a property of this operator that are part of this functor, the functor H. Then I think that with these two elements, we can proceed to see this the Grassmann algebra implementation in a more specific way. And then we arrive here to examine the two algebras here in this implementation.
So this construction for the bilinear form is built from the tensor product, I guess.
It's built from the tensor product. Yes, yes. Mm-hmm.
But from it's the tensor product of an element and its dual, right? Always. Like from your previous diagram, you have these two. Yes, so you have say from lambda and lambda star, we can produce a bilinear product.
Yes, yes.
But these bilinear forms are yet another So if we were to write lambda tensor lambda star, right? Here it's an object not in either of these. You know, such a thing. This bilinear form is yes.
Yes. But here we have evaluation. That is a relation between lambda star and lambda.
But this evaluation is defined in a natural way without the introducing a bilinear form.
Yes, yes. But if I one implementation of this evaluation is I don't know. Okay. Sorry, I need to write in a different way because I need that I think to write this in terms of a pair alpha A, for example. Yeah, I wanted to use the notation that used to be used by Professor Osiewicz, but it is difficult to write that. But then this is getting alpha A, for example. And this is a bilinear form. But it depends that how I define evaluation. Then if I define evaluation in terms of bilinear forms, and then how I use it here, bilinear forms, I have not notation here. No, only bilin. No, but if this means that F have the bilinear property that we know. Yeah. But here I have select the evaluation using sorry, something wrong here. Sorry, it does not permit me to write something wrong. Sorry. Oh. Can you listen to me?
Mhm. Oops.
And I have some problem here with my presentation, and this was closed. Then wait a moment, please. Okay, I lost all that I was writing, but I think that this was an elementary thing that I was writing for the idea that evaluation are the bilinear forms.
Mhm.
Huh?
Yes, I think it's clear.
Yeah. Okay. And then with this now I can I go to exterior algebra of multivectors, defining the principal properties of this, how we know, and for the same for here is an important thing, because the definition of this exterior product of vectors is based in this symmetric part of the space of tensor product without the antisymmetric part. But I have here then that we have two kinds of products in the with the vector forms. With the vector forms, we have asymmetric part and an antisymmetric part. Then, because of this, we have adjunctions and we have exterior product in this vector algebra. Then I think that this is important because I consider that this is part of the idea that using these operators, we can build the Grassmann algebra, but we can only build the antisymmetric part of the vector of the multivector forms, but we cannot build the dual space with these two parts of the operation.
Yes.
Yeah, then I think that it's important. And here we have now the exterior algebra of multiforms that is in the dual space. And then with this definition, we have the algebra of scalar forms using these bilinear forms that we have defined based in two okay, here we have defined the product and the required properties for this algebra. And then we can speak again of duality.
But this is a uniquely defined bilinear form, right? It's
yes, here only by bilinear forms. Yes. I left this defined by bilinear forms because this property of the tensor product, because the tensor product give to us a vector space and a bilinear form. Then with this idea, I left the definition in terms of bilinear forms. I don't know if we can change here the. Okay, maybe we need to use here the D operator for building higher degree, but I don't know how make a general definition of this multigrade space without the bilinear forms. I don't know. Maybe defining the operators of, but I think that this is to go back to this kind of construction process. Okay, with the required correction here.
Yes, the dual. Yeah.
This one. Yes.
The bilinear form allows to go from the space to its dual. This one that you just defined allows you to go from
the bilinear form here. Here.
This one, yes.
Yes. Mm-hmm. Mm-hmm. Yes, because this is we have the scalar form related with a vector form.
Yes.
Well, yes, because he's a pair of vectors here. And then, okay. Mm-hmm.
Yes. This it reminds me of a terminology. It was something called musical isomorphism. Do you know this word?
Please repeat the word, please.
It means there is isomorphism between the vector space and its dual. And
yes.
This isomorphism is sometimes called the musical isomorphism. And we think of it as raising and lowering, in the tensor.
Okay.
Tensor form. So it's the thing which, when you multiply it, raises the index on the tensor, or it lowers the index on the tensor.
Okay.
But it's uniquely defined in Grassmann algebra. But in the Clifford algebra, this the corresponding bilinear form is given directly. Is not natural anymore. Is no longer You cannot define the unique alternating bilinear form in Clifford algebra. That it must be given separately.
Yeah.
Whereas in Grassmann algebra presented this way, there is this intrinsic natural bilinear form that allows to map between the space and its dual.
Okay. Okay.
So for that reason, again, I'm not clear to me how you can consider Clifford algebra to be a subalgebra of this. Right?
Okay. And, my idea, I think that I can speak some on this, but my idea is simple because the Clifford algebra is self-dual. Then, if Clifford algebra is self-dual, this means that in the building process, for example, if I have a Clifford algebra, no, sorry, I'm going to use the Clifford product, then E1, E2, and I think that the dual of this is E1, 2. Then, because E1, 2, in fact, is a bivector. And here inside the parentheses, we have a product. Then I think that the dual is built in this way. Because of this, I think that if we have a E1, 2, and multiply by E2, for example, we have E1. Because here we are multiplying by the dual. Then this is equal to the evaluation of E1 to E2 is equal to this. And this is the idea that I have. I need to write this in a clean way for.
Could you just rewrite what you just wrote? It seems not clear to me on the screen. The last,
yes,
you said evaluation.
Yes, I'm going to erase this. Here I have, I'm going to put evaluation, for example, in EI, EJ, and then I'm going to put in this way. I individual, J. And this is the idea that I am using for evaluation. And then, for example, if I got to write side of this, if I use evaluation of E one with E 1, 2, then by definition, this is E1, E1, 2. But this gives to us E2. Okay, and this is the idea that I am trying to formalize.
But you need a representation of E1 star, E1 dual, right? Dual of E1 is.
Yes, but my idea here is to use the, I'm going to put the black words better because I have, it is better to have more space. Sorry. And yes, and the idea is to start with the, for example, if I use a number actually for element, for example, it's a linear combination of and so. Then the idea is that we have a unique representation of this. Sorry, if we have a base related with this dimension, with the dimension of this algebra. Okay, then for example, in 3 dimensions, and the base here is but we can have a different representation here that is, for example, using another base that is E01, E12, E20, for example. And then an element here can be represented with this. And the idea is that this is the dual. This is the dual of this. Then the idea is because in the Dedekind book of um, what's the title of this book? One dimension function. The, no, it's algebraic functions of one variable.
Yes.
In this Dedekind book, he start using the terms, the concept of duality. And he used the concept of duality speaking about one base for the space of polynomials here. And he speak about a complementary base. And a complementary base is the reciprocal base of the original base. I think that it is similar that we used to use in solid state physics, for example. When we speak about the base of the of the solid, and we speak about the complementary base.
Mm-hmm.
Then it's the same. In fact, is the same. Then we can find different kinds of representation for the system, and one is the dual of the other. If we write this in this way, then I think that the problem of duality in Clifford algebra is not present, because the duality is have a good definition there, and the only thing is that the Clifford algebra is self-dual. And only that. Then I need to explore these ideas more, but I think that we can write in this way. And in this sense, because all of these are elements of being, then we are in the lower part of the Grassmann complex. I think that it is important to explore this, because then when we use Clifford algebra for representing some properties of physical systems, I think that we are losing information. And then it is needed to use a more complete algebra for explore these properties. But okay, that is only one idea.
Yes. So maybe it's that sense that you said that Clifford algebra is a subset. I mean, it's it's not, maybe this notion needs to be explained more clearly, that it's not not a subalgebra in that sense, but it is a special case of the
Okay.
so it's a special case in which the is self-dual.
Yeah.
So here you don't explicitly introduce arbitrary metric, for example. The only metric that you involve is this bilinear form that you construct.
Yes. Yes, there is not metric because I am using evaluations and only operator of creation and annihilation.
But I think you can, it's okay to introduce it in your slides when you introduce the construction of the bilinear form. You call it psi, right? This this bilinear form can be specified separately. It can be given as the metric. Rather, it isn't necessary to choose only this natural bilinear form, but given any bilinear form is sufficient to construct a Clifford algebra.
Okay.
See, here you construct one unique Clifford algebra that has this uniquely defined natural bilinear form. So it's you could say without loss of generality, because you it's convenient for you to do that, but it isn't necessary, I think.
Okay, and I think that I can work in this idea, and maybe I can prepare some slides for the next meeting.
Yes, yes, I think I like to continue this for sure. It's but I'm thinking again that to introduce this concept of duality in a way that is compatible with what Dr. Sobczak is doing, it seems difficult to me. And I know that you have some questions in our last meeting with Dr. Sobczak that about the notion of local duality, that the idea how we can really have this notion of local duality.
But I think that with these ideas, I think that have not the sense to speak about local duality. I think that it is not necessary because how I understand, we can, for example, in 3 dimensions, or maybe I speak about the 4 dimensions. I can take 2 planes and then think that one is the dual of the other. Then I am splitting the space in two spaces that are, how you say, the intersection is null between them. And then we can think that one is the dual of the other. And in fact, I don't remember there is a paper that is discussed these ideas in a clear way. Then I try to find this idea and present them, because in this way, then an space can be split into two parts, and then one can treat these two parts like the dual of the other. But then you need that the splitting of the space give to us an exact sequence. Then the one is the kernel and the other one is the image, and then the image is exactly the same dimension that the kernel. In this way, it is possible to think of one part of the space like the dual of the other. And I think that the idea of Professor Softic, Garrett Softic, is related with his idea of local duality.
And so, in other words, you would say that his definition of local duality can always be rewritten as global duality, right?
Yes, this is the idea. Yeah, this is the idea. Mm-hmm.
So it doesn't, this notion of local duality doesn't add anything. It's not.
Sometimes maybe it's important the concept of the vector better than the product of two vectors, because there are some, for example, physical objects that are related better with the concept of bivector, or bivector, sorry, bivector. But I think that in this way, this is important. To speak about two different kind of space with different properties, or subspaces, better. Mm-hmm. I think that it can be useful in this way, but I don't say that one is the dual of the other. For example, in three-dimensional space, it's not possible. Then, but I think that it is needed to work more with these ideas. Mm-hmm. Mm-hmm.
Okay, well, I think it was a very good continuation of your lecture from the last time. I just checked my email. I don't see any email from Dr. Sobchik, so I will send him a message just to ask about his plans. I understood that he would be prepared to give a lecture today. So perhaps he has some problem. In that case, if he does, I think, want to give some presentation, we could continue with his presentation in 3 weeks' time. Or depending on his answer, of course, then I would be very interested to continue what your subject, Jesus. I think it's
okay, Oscar. Thanks. Yes.
I think it would be very good to try to express this concept that you just mentioned, that the local duality is not necessary. Maybe that's too hard to critical a way to put it. It's not so much not necessary, but it can be a special case of the global duality.
Okay.
I think it would be good to see that as a more formal statement, as you just suggested.
Okay. Yes, I try to include that.
Okay. Well, I think let's say that's the end of our meeting for today. I see Brian was here, but he hasn't asked any questions or spoken, so I'm not sure, but I'm glad that he was here for the meeting.
Yeah, I actually have a lot of questions, but I was going to suggest to Professor Jesus maybe someday make a book with all these ideas, because there are some concepts that I'm missing to comprehend well, to understand the whole structure of what is being explained. So I think with the book, you have like a lot of space to be detailed about everything, and that could help people like me that is missing like a strong mathematical background. But in general, I think I get like some ideas, but I think it was good.
But it's Brian, I think it's the same comment that I started with, saying that the tools are interesting in themselves, but they are abstract without, if you don't see immediately their application. But in terms of writing a book, I think it's probably necessary to say that there are already many books on category theory.
Yes.
But none of these books, for me, ever end up being the one book, that is necessary. But I think Levere has some, Levere's book, I think, is one of his books anyway, presents many of these ideas from the beginning, from a but
Yes,
maybe it would be good, Jesus, if you could say add some suggested references, like to your slide, like to say to find out more about this use of a junction, for example. It's good to use some reference that you prefer.
I think that I think in terms of write a draft of a paper, and maybe it was in this draft an appendix with some of the principal ideas that are ideas and concepts that are used for this formalization. and then I think that we can write a draft, and I can circulate with us for comments and modifications, something like this.
Yeah, that would be great. Yeah, really, it would be very useful, I think.
Yes. Okay.
Yeah, sounds good.
All right.
Okay.
Well, I'd be looking forward to continuing our discussion in 3 weeks.
Okay.
And I hope your weather in Mexico improves and not so hot.
Yeah.
But,
Thanks. Because.
I hope
Okay.
that too. So
for me
see you
now,
then.
I'm still hoping that it gets warmer here. I would like more warm weather. I'm sure that's
Yeah,
going to come also.
I think on Monday was like the highest temperature reached on Ciudad de Mexico, which is where I tend to work, and it was like crazy hot. So I hope that we get some more like cold days, and you guys can have more warm
Yeah,
days.
we'll
We can
trade.
change.
We can
Yeah,
exchange. Yeah,
yeah.
a good idea. Okay, see you in 3 weeks.
See you in
See
three
you.
weeks. Take care.
Bye.
Bye bye.
Thank